Okay, so welcome. Assignment 9 has been uploaded. Deadline is the usual Monday. And just to look ahead, we have one more assignment and we have 4 exercise classes left and 4 lectures left. Okay, so we will have many things to discuss. I think it's very fun stuff to share with you. So let me try my best to get through the remaining of the course. And the graded midterm answer books can be collected from tomorrow. So I will send some emails after I discuss with the TAs, and I will tell you where to collect your answer books. Okay, only for tomorrow's slot. And we will see how it goes. And I will also explore the way to return, to announce the midterm score using Blackboard. Okay, so this is, so check your email, check your official email. Okay, if you have any question, please ask now. Otherwise, I want to start. Okay, let's see what we did last time. Okay, before the break, this was a long time ago. It feels long. It's about, what, 3 weeks ago, even less than 3 weeks. What did we do? We started talking about indistinguishable particles. So we begin by writing down the solution of the Schrodinger equation. We didn't solve it because it's a well-known result. We treated the problem of indistinguishable particles like that. Okay, we have an infinite potential well, and then we write down all the energy levels, and then we discuss that problem. Okay, that was even way before the last lecture. And after that, in the previous lecture, the very last lecture we met before the break, we mainly discussed how to test the entire framework, and we decided that we can the problem we set up is actually the problem of the ideal gas, weakly interacting and very dilute, and this is actually all the attribute of an ideal gas. And we also decided that this is the problem for the monatomic case, because we only discussed the kinetic energy, the translational kinetic energy of the particles. And as an aside, for the exercise class this week, we are going to discuss the diatomic gas. Okay, there the problem is actually more complicated, and you are very encouraged, you are welcome to really read these materials guided by the TA. So there you have diatomic case. What happens to the partition function? Okay, so that is something I don't have time to cover, but you will see the full treatment in the exercise class. And maybe just very briefly, for that kind of case, you need to consider the rotation and the vibration. So the energy will be different, and you have more features to consider, and therefore the partition function will be more complicated. And I think when you attend the exercise class, you need to pay attention on how to still extract the ideal gas law. Okay, you should not have the impression that if we make the problem more complicated, we have more terms in the partition function, the ideal gas equation of states will be changed. We know it won't change, right? The ideal gas law you learn in high school, you learn it for all kind of ideal gas, helium, nitrogen at high temperature. Okay, and now, how do you do it properly using statistical mechanics? And that will be discussed. Okay, so we tested it on monatomic ideal gas, and this is what we have. This is what we did. We evaluated the partition function, and this is how we did. This is the single particle partition function. This is equation 10.38 in the lecture note. And you can see this is the continuum equivalent of the way we treated the partition function. If you remember the definition for the summation, we have sum over G sub J, epsilon J, and then exponential term. Okay, so if we have a lot of energy levels that we can treat as continuum, this is the formula. Okay, this is rather important. And after many steps, you will get this result. Okay, and here, when we got this result, I ask you one question. I ask you, what is the unit of the partition function? Okay, and you told me it's dimensionless. And because this product has to be dimensionless, we are able to define something called the quantum concentration. So this is the quantum concentration. And this all came naturally from this treatment, right? We just rearrange, group together the terms. And I explained in the last lecture why this is quantum. And I won't repeat the argument again. But today, this is very relevant to us, this n sub q, because when we decide whether a particular system of particles, indistinguishable particles, is classical or quantum, we really use this n sub q as the benchmark. Okay, so if the concentration is very high, higher than the threshold, then we have to consider the case that the particles can begin to compete for the same energy level. Right? Remember, this is our assumption for this part of the course. We assume we have way too many energy levels that are accessible to the particles, but we don't have that many particles. So my example to you, for you to remember, was if you have, for the calculation I did, if you take in the population of Hong Kong and there are only 35 cars, so that is the dilute system we are talking about. But you see this NQ, you can have a preview now because we are going to deal with this soon anyway. How do you enter the regime where if you have the fixed n, how do you enter the regime where classical statistics begin to fail? So one way to do that is to see how can this NQ becomes modified. Okay, so and if you're in the dilute case, your n will be much lower than NQ. But now I can make the NQ n sub q lower by cooling, for example. And this is indeed the case. If I take my helium gas and begin to cool down, you will see this calculation will begin to fail. Okay, so this is the main topic of today. Is actually we are going to look at the case when we need to worry about quantum statistics. And then I won't say too much because you will practice in assignment 9. You will be asked to calculate n for some spatial cases and compare with the appropriate n sub q. Okay, appropriate n sub q means you need to put in a correct mass, correct temperature to estimate this. Okay, so coming back to the part before the break. After we get the partition function, we can turn on our sausage machine again and calculate U. We indeed correctly recover the internal energy for the monatomic gas. Right? This is something you learned before. 3/2 nkBT, very famous result. U, in this case, the system has 3 degrees of freedom. So you have 3 here, 3 times 1/2 kBT per particle, and you have n particles. The other thing is the internal energy is only a function of temperature and nothing else. Everything else is constant. And I asked you to evaluate pressure, and we did it together. And we realized after, again, we turn on that sausage machine, we will recover this result, which is not surprising. It better be like this. So you have your PV is nkBT. Okay, by the way, I want to say something. In your midterm, something I don't quite like to see is the following. Nothing wrong, but you will get confused yourself. you know, we write ideal gas law like this. And if you want to use this form, or if the question is written in this form, then stick to this form. Don't mix. Sometimes in the same question, you mix two, and then you don't realize they are the same. And then you carry all these n's and the kb and the gas constant around. This is something I have seen when marking your midterm. Okay, so this is something you can pay attention. Okay, what was the next step? The next step was really the key. If you put in the correct form of the system partition function, or I also call it the partition function for an assembly of particles, you have this n factorial, you get the correct form of Sackur-Tetrode equation. Okay, this is here. And again, this is important, and we justify that you indeed need this n factorial. How did we do that? We did it by demanding that the entropy correctly follow the property of an extensive variable. Okay, so this is done last time. And the other thing which I didn't do, but it's kind of trivial, you can analyze a situation for an adiabatic change of volume. Adiabatic change of volume. Okay, here again, this is a related comment. In midterm, when I give you a very precise form, actually I gave you exactly this. I gave you this as the starting point. It's not enough to give me PV of gamma to the gamma is constant. Okay, that is not enough. You need to find out this gamma here. Okay, what is this gamma? Okay, when I give you a precise form, you can give me a very precise gamma here. Okay, so this is an exercise which you can do. You can do exercise. How do you do that? Actually, it's a change of volume. Okay, you change from V1 to V2, or you change from state 1 to state 2, and it's adiabatic reversible change. So your entropy will be the same. So you basically just have a very trivial exercise to do, but please do it. And then from there, you get a precise gamma. You get this with a particular form, precise value, with precise value. Okay, this will take you 5 minutes or less. You can try this. We didn't do it last time. Okay. So up to this point, it was everything we covered before. And there's one last piece which I didn't cover, but this is actually very simple, very straightforward. It sounds like a very big topic, but actually from our treatment up to this point, now what is this? From our treatment, we know how to write this down. Okay, so this is the continuum form of NK, right? So how many particles in this K bundle? We derive the result. We know this is this result, KBT. Okay, we derive this. And if you switch to the continuum form, then you have this GED replacing here, and this E sub K becomes continuum. So it's this epsilon sub K would just become epsilon. And then you have N of epsilon D epsilon. Okay, so this comes from here. You might want to note this. And the expression of G, this is coming from our analysis of the density of states. Okay, so this itself is again, well known. So you just plug it in. This is the same form as the one we use for evaluating the partition function. Okay, so this is, you just really plug in that expression of G of E, G of epsilon, sorry. When I say E and epsilon, just think of it as energy. Okay, so this form is here, it's given here. And it's a well-known function because this is a square root of epsilon. Okay, something I kind of need to remember because of my research. We use it all the time. Okay, in 3D, this is proportional to square root of epsilon. Okay, the only thing which you may not remember, or maybe you know, is how to write this A. This A is the normalization factor, but you can also write it as n divided by the partition function. And actually, when I introduced this before, I already say this. And that is how I explain the normalization. Okay. And from here, if you know this form, you know this Z from 2 slides before, you can actually write n divided by V. Remember, this is proportional to V times NQ. So basically it's like this. Okay, so but this is not a very useful form. This is the full expression, 2m pi kbt. Okay, so when you plug this in, now you have to work a little bit harder, but not too much, no integration. You just need to tidy it a bit, right? You see, you have 2m here, you have 2m here, you have 2 pi, you have pi, you have kbt. So the end result is given in the note. Actually, it's not too long. Let me write this down. So this is 2 pi n pi kbt. You have this square root, you have this exponential. You have this Boltzmann factor. Okay, so you see there's a d epsilon here, so there must be a d epsilon here. Okay, now in 2041, I believe you have a big derivation of this. Okay, you did it maybe from first principle. Okay, so here up to this point, I did it using the particle in the box treatment. Okay, so up to here, nothing new, really nothing new. And how do you quickly get this result for free? You do it like this. You take this expression and then just change it to n velocity. This is energy, this is velocity. And this will be the precise form you need. That gives you the Maxwell Boltzmann distribution of speed. Okay, how do you do that? How do you change from epsilon to V? So you do that simply by paying attention on the form of energy. So here we don't really have much choice. We have to associate this energy exclusively as the kinetic energy of the particle. Okay, so you go, whenever you see epsilon, you just replace by the form of epsilon. And don't forget to manipulate the d epsilon because you want dv, so there will be a 2v dv, and not too difficult to deal with. And in the end, this expression is exactly the expression you want for Maxwell-Boltzmann distribution of speed. Okay, so this is again important. In my opinion, it's important because again, this shows you we have done something correct. Right, this is the right treatment. Okay, so in the note, I will ask you this expression is given in the note. Okay, so you can look at it and don't just look at it, try to plot it, because this is something well known to you. You learned before, so you can plot. You can play with different fixed temperature. For example, you do a 300 Kelvin and 200 Kelvin and see how this distribution sheet. Okay, and then here you will hopefully see that the shape is not quite symmetric. That's why you can define the most probable speed, the average speed, the root mean square speed, and all these speed will be a little bit different. Okay, so this is something, a to-do list for you. Okay, so I think I don't need to show you that figure. You know it quite well. It's a slightly distorted bell shape, if you like. And what I want to do instead is to start to talk about quantum statistics. Okay, so this is a very brief chapter. This is chapter 11. Chapter 11. Now, I don't really need an entire chapter for this. So I included some material just for completeness. Because I believe you have learned or you are learning this part in quantum mechanics. Okay, this is about the exchange of particles. And what I care about is the statistics. How do I come up with the correct statistics to do things? Okay, so when do you need quantum statistics? Let me rewrite this formula again. This NQ, N sub Q is what you should pay attention. This one. Okay, so what we want, when we cool down, this will become small. When this becomes small, this threshold will be different. And if your concentration is larger than the quantum concentration, you need to seriously consider the breakdown of the classical statistics. Okay, this is one way to look at this. The other way to look at this is to go back and think about how we set up the problem for classical statistics to begin with. We look at the number of energy levels, energy states accessible to the particle. And back then we set a temperature scale, right? We say, okay, I'm going to look at 300 Kelvin. At 300 Kelvin, for this kind of energy, thermal energy available, how many states are possible for the gas? And then we realize this is very dilute. Okay, now this energy scale is nothing else but this KBT. And if I lower the energy, then of course, even if the energy states remain the same, but the energy states accessible to the particles will be greatly reduced at low temperature. And that is when we need to consider the breakdown of classical picture. Okay, so even for the quantum picture, we still have more work to do before we can write down the statistics. So first, we need to worry whether we have bosons or fermions. Okay, and remember, these are still identical gas particles, but then they have very different exchange properties. Okay, so we need to let's spend some time to look at this exchange of identical particles. I will be brief. Please, in the chat room, tell me whether you are learning this right now or you have learned before. In your other courses, are you covering this material now? Okay, Good. So I will look at some cases that are simple. Okay. So if we have two particles, let me just take the simplest case to begin with. So let's say I can label the first particle as phi1 and the second particle phi2. Okay, and I'm going to give them some coordinates. So I'm going to label this R1, but I don't want to put a bar here because I don't want to clutter my whiteboard. But this R1 is some kind of very general coordinate. It can be spin coordinate. It can also be spatial coordinate, like the position in the space. Okay, these are all grouped as this notation R. Technically, I should put a underscore, but I don't want to do that for the reason I just explained. Okay, so these are identical, indistinguishable, and non-interrupting particle. Okay, so as usual, if I ask you what is this square, this is the probability of finding particle 1 at R1 or with this coordinate, generalized coordinate R1. So this is some kind of probability of finding particle 1 at R1. Okay, and now if I treat this collection of particles as an assembly, then I need to describe the collection of them, right? So I can write down a total wave function for this assembly of two particles. Okay, so I'm going to label this as R1 and R2. Okay, and now this is how we discuss the exchange. If I exchange the two particles, that's to say, if I put the particle originally at R1 and I move it to R2 and vice versa, then I will get another wave function, and that will be R2, R1. Okay, but these two particles, sorry, I will write it here. Sorry, I don't want to do that. R2, R1. But I already told you the particles are not distinguishable. So after I exchange, I look at the system again, I cannot tell the difference. There's no way that I can tell the difference between them. Okay? So can I convince you that I have to write an equal sign for this two-wave function? Okay, tell me, do you accept this? Well, in private, okay, more. I want to see. Quick. This is rather important. Okay, the answer is a big no. Never. This can never be the case. Okay. What we can only say, at most, is this. Okay, I exchange two particles. The only thing I can interpret this wave function is to use the probability. Okay, so this is the case. If I put that equal sign, it was a big no. Okay, so in this case, this is where we get this symmetry, anti-symmetry wave function coming in. Because of this, if I want to write the wave function itself, if I insist, I don't want to look at the probability, I just want to look at the wave function, I acquire this plus and minus sign. Okay, so this is the way to argue about this. The other way to do this You can, if you want, you can also do it this way. Now I can say, if I exchange a particle, so after I exchange, originally is R1, R2. So now I exchange the coordinate of the particles. I have to acquire a phase. Okay, so this is allowed because okay, if you square it, the phase factor disappears. Okay, but I don't want to argue it this way. I can also say another thing. I can say, okay, now if I swap it back, R1, R2, I will acquire another phase, right? Whenever I swap the particle. Okay, but if I look at this left-hand side and the right-hand most expression, I know they must be equal. So this e to the I phase square has to be 1. So this is the same thing. This is the same way to say that this phase factor reduced to plus and minus 1 here. Okay. This is a trick question I ask. If you get it wrong, don't worry. But from now on, it cannot be wrong anymore. Okay. And this plus and minus leads to two types of particles. Okay, one type will exchange with a plus, the other type will exchange with a minus. And we need to look at them case by case from now. So this is what happens when you simply look at the exchange of the particles. So from here, you deduce that there are two different signs. Sorry, I want to copy. Okay, so remember this is the sign we need to pay attention for the remaining treatment. So let's move forward. And from quantum mechanics that you are learning now, you know that the solution to the Schrödinger equation for this two particle assembly will have to satisfy some kind of linear combination. So let me write this down. I can write R1, R2. This is the solution to the Schrödinger equation. This is the wave function for the assembly. And I want to write it in terms of phi 1 and phi 2. Okay, so maybe I can write it like this, R1 and phi 2. Okay, but this is not enough, because if you write it this way, there's no way to put in this sign factor. Okay, so I think in your quantum mechanics course, you know how to treat this kind of thing. So I will just tell you what we are after. What we are after is this. So if this is a solution, it can be shown that this is also a solution. Need to be careful with, so this is 1, 1, 1, 2, okay? And if you want to respect the sign due to the exchange of the particle, then you can actually integrate it here. Okay, so if you want to have an anti-symmetric exchange, that is to say, after you change, you swap the particle, you acquire a minus sign, then you just put minus here. Okay, you can verify this yourself. And if you want to normalize it properly, you have this 1 over square root of 2. That's it. So this will exchange. Once you exchange, there's a minus sign here. So the wave function will change sign. Okay, so this is for fermion. And for boson, you will put a plus, which means it's symmetric. After you change, you just get a positive sign. They look the same. Okay, so this is enough. but a bit too boring. It's only 2 particles. And how do we look at a more complicated situation? Let's say we have 3 particles that we can exchange. Using the same notation, I'm going to use phi, phi1, phi2, phi3 to denote 3 particles. And the generalized coordinate will be R1, R2, and R3. Okay, so by the same argument, you know this is only one of the possible solution. So that's to say, if you look at the 2 particle case, this is one possible solution, this is one possible solution. But if you want to respect the exchange symmetry, you have to build your total wave function like this. Okay, so if you go to higher number of particles, you have the same problem. This is only one possibility. So this is one possibility, and you need to build something that allows you to discuss this exchange symmetry. Okay, and the way to do that is to use a slatted determinant. So the full answer here is slatted determinant. Okay, I will do fermion first. Boson, we will deal with this later. Okay, so how do you systematically find all these terms? Now, I just want to show you how to think about this, and you can find all the terms yourself. So one thing you can do is this. You can do it systematically by, for example, keeping the third one unchanged. So the third particle will be sitting at R3. You don't want to deal with them. And then you change the other 2, namely phi1, phi2. Phi2. Okay, and you swap phi1, phi2. You put phi1 at R2 and phi2 at R1. And you acquire a minus sign as from our previous discussion. Okay, and you keep this unchanged. Now you expand this, you get 2 terms. But there are more terms to discuss. Altogether, you have 3 factorial permutations. So the total number of terms, will be 3 factorial. So you have 4 other terms, unique term that you have to try to figure it out. Okay, you can try to do it yourself. Another thing to observe is you look at this permutation of R1, R2, R3. Let's say you write phi1, phi2, phi3, you line up them according to this sequence. Then you look at R1, R2, R3 and see whether this is a cyclic or not. If this is following the cyclic permutation, you get a plus sign. Otherwise, you get a minus sign. Okay, there's another way to make sense of this whole thing. Because I don't want to just write down the slatted determinant and then you think this is just some magic. But actually for a small system like this, you can actually understand all these terms. Okay, so for 3 particle system, the total wave function is simply written like this. One, two, three. So 1, 1, 2, 2, 3. Oh, okay. So this is the determinant. R2, R3. R1, R2. Okay. So this is the answer for this question. So you have altogether 6 terms. As you can know from matrix theory, once you expand this out, you have the terms you want. Okay, so I want to generalize it to n particles right away. So I'm going to In green color, this is what we need for 3 particles. So if I have more n particles, I will run from 1 to n. This is R1. And then I will run from here. This will be 5n of Rn if I have n particles. And this determinant will run from R1 to Rn. Okay, and this is the correct wave function for m particle. Okay, and now further I will tell you a little bit more for you to see that this is a correct form. Okay, so this is a matrix, and we evaluate the determinant of this matrix. And if you do it properly, you know you get this sign difference, right? The easiest one is to look at 2 by 2, and you will very quickly convince yourself that this reduces back to the correct wave function we discussed up there. Okay, but if you look at this is enough to tell you a few things. Okay, if we interchange 2 rows of, 2R, let's say we swap 2 particles. Okay, so how do I swap 2 particles? I would just move all the R1 to R2, all the R1 to R2. Okay, and you will get a minus sign by metric theory. If you swap any 2 rows or any 2 columns, the determinant changes sign. So this anti-symmetrization is automatically built into this letter determinant. Okay, so this is good. All the exchange property we discussed is correctly accounted for. Okay, so you will, if 2 rows, 2 rows are interchange, you get a minus sign. And more importantly, if you have 2 particles occupying the same state, so 2 particles occupying the same state, let's say 2 and 3, particle 2 and particle 3, for example, this and this occupying the same state, then you have 2 identical columns. Okay, what do you have? Once you have this situation, your total wave function goes to 0. This is nothing but the statement of the Pauli exclusion principle. So you cannot have 2 fermions having exactly the same quantum state. So this is Pauli exclusion, Pauli's, but it's okay, Pauli exclusion principle. Okay, so this is really a very good wave function here. Okay, how do you deal with boson? The boson case, if you go to 2 by 2, I won't write this down, it's in my notes. If you go to do 2 by 2, let's go back here, somewhere here. You don't have this minus sign. As I already explained, you don't have this minus sign, you just change it to plus. And how do you deal with this n particle case? The way you do that is you just expand the determinant like before, but whenever you see a minus sign, you change it to plus. And whenever you see the plus sign, you keep it. So this will be the case, the wave function for n bosons case. And then for the 2 by 2, and you can you can also justify that if you have because for the two for the two boson case, this is the simplest. Sorry, I keep overshooting. If you have a plus, and if you have phi 1 equals phi 2, you will not have a total collapse of the everything in the square bracket. So in this respect, if you have boson, you can actually occupy the same quantum state. Okay, because you don't have cancellation, the wave function will not go to 0. You will not have the case that you cannot find. You have 0 probability of finding the particle. So for boson, it's okay. You can have more than one boson. You can have many bosons in the same quantum state. Okay, so remember the Pauli exclusion principle and Pauli exclusion principle for fermion. And for boson, you can have many particles occupying the same state. And based on these two statements, we are going to build the statistics. Okay, so I propose a break now. Now, before you go, after the break, we are going to start writing down the statistics based on these two statements. And before you go, Vivian told me there's a class evaluation today, and you should have received an email, right? Correct me if this is not today. According to the email sent by Vivian, there should be something for you that you can have access. It's a one-click access for course evaluation. Is it there? If not, I will have to call Vivian. Okay, now do me a favor. We are going to take a slightly longer break. Now it's 12:26. Let's take a 10 minutes break or even 15. Do me a favor, when you do the break, when you have the break, fill in this evaluation. And then let's get this done, and then we will come back and continue our story. Okay, so now it's 12:26. Let's start again at 12:40. All right, welcome back. Okay, now we are ready to start to talk about the statistics. So here we go. So they are Fermi-Dirac versus Bose-Einstein. Okay, so there are two different statistics to use. Okay, so that picture of K bundle applies. So it's the same thing as the classical case, but now we need to do the counting based on what we learned in the first part of today's lecture. Okay, so just to remind you, I drew this kth bundle before. So this is one of the bundles. So this is the kth one. Okay, and then kth bundle, and we have G sub k states, and then we assume that this epsilon sub k is a good representation of the average energy. Okay, so this is I don't know where I should draw. Maybe I do this, and you know this is energy scale, so this is epsilon sub k. Okay, so this is the setup we have, and now the question is how do we distribute n sub k particles in this bundle? Okay, so let's start from fermion. No, actually, I want to start from boson. So for boson, uh, actually the problem is the same as before. So if I have NK particle, NK, so let's start from boson. So for boson, if I have NK particles and GK states, then we have GK minus 1 partitions. Okay, so we have NK boson, GK minus 1 partitions. And any arrangement is acceptable because we can put many bosons in the same state, so we can have many bosons, and then no boson, no boson, no boson. Fine, this is okay. This is acceptable. So this is allowed, one of the states. Or we can have one boson here, one boson here, two bosons here, and then no boson, and then somehow one here. Okay, so these are different ends. So I don't want you to complain about this. Okay, I put one here just to please you. This is also allowed. Okay, so how do I count? The number of arrangement for this K bundle is identical to the case before. Okay, how many objects do we have? We have NK plus GK minus 1. So we have this many bosons, this many partitions. So altogether we have this many objects. Okay, so if I only look at the different ways to assign position to these objects, I have this many. But that's not enough because we can not distinguish between different bosons. So we need to divide by this NK. And we cannot distinguish between the partitions. So we have to do this. Okay, so this expression you see here is identical to before. But be careful. For the classical case, we started from here and we began to make approximation based on this. But now you don't need to make approximation. The only thing you can do is to realize that GK is very large, so you can ignore this one. So this is the best you can do. And that is the only thing you should do. Okay? And that's it. This is for boson. Okay, I will need this later, so let me make a copy. And now let's talk about fermion. Let's write the fermion in different color. Green, I like green. Fermion. Okay, now I have NK fermion. And how do I write the omega K for fermion? If you haven't seen the note, this is something for you to think. I won't have much time, but I can give you 1 minute to think about this. And GK, G sub K states. And how do I write? Omega K for fermion. Any idea? Now, this is like the coin problem, right? This is something we discussed before. For the coin problem, just think of it as head, this is tail, and this is head plus tail, right? So you have this, the way to think about flipping the coin. That's why we spend time to flip the coin. And now this fermion case is also a way to flip the coin, but if you flip it a bit differently. Okay, the way to do that is this. I will look at it like that. I will say a given state is either occupied or empty. Okay, so let me let me write the coin problem slightly differently. Okay, so if I look at this number of states, because of the Pauli exclusion principle, I cannot put two fermions in the same state. So I can put one fermion or no fermion. So in this case, the binary scenario is whether you have fermion or you don't have fermion. Okay, so if you have fermion, you put NK. Okay, these are the states with fermion. And the empty one will be the one without. So it's GK minus NK. Okay, and the total number of states will be the sum of these two. It turns out to be GK. Is it okay? Make sure you, you get this. Okay, I have GK states. I can either put no fermion. Okay, so there are that many of them without any fermion. I cannot tell the difference apart. So I have to divide by this GK minus NK factorial. And I have this many of them occupied by one fermion precisely. So I have this. Okay, so this is the starting point to do the statistics. Actually, we need to first learn how to count. Then we work out the equilibrium distribution, like exactly the same steps like before. But this is really the entry point. If you get this wrong, I guarantee you, you get the wrong answer. Okay? Is it okay, guys? This is the difference. Okay. Now, let me say this again. Do not make approximation. This is again strangely every year I see this. People make approximation after this step. Then you are asked to give the Bose-Einstein distribution, and then in the end you end up having the Maxwell-Boltzmann distribution. The Maxwell distribution again. The reason is back then we really start from here and make approximation, and then approximation being that we have way more GK than NK. Okay. All right. So you will follow the same steps. Use the Lagrange multipliers again to get the equilibrium distribution. So these two are really parallel. You will see the steps that you can recognize. So I'm only going to do one. In the assignment, you are asked to do fermion. So I will do boson. Okay. So I will give you the Bose-Einstein distribution. Okay, so that is why I keep this slide here. Okay, so let's proceed with the distribution. This is a bit better, this green. Okay, so to get the distribution, okay, now to get this is Bose-Einstein equilibrium distribution. You follow the same steps again. First, I need to know the total omega, not just for omega sub k, but for the entire system. And I argue that this has to be written like this. Okay. So you just do the, you just follow it and do the log, and then you use a Stirling approximation, and you get d log of omega sub b, all the same procedure. Okay, so let's begin. We need a lot of space, so let me write here a little bit small. Okay, I'm going to write to first evaluate this because I want to maximize this. Then I might as well maximize log because that's we already know this is the more convenient things to work with. Once I take the log, I convert this to sum of log omega sub k, which is the sum of log of this whole thing in orange color. Okay, so I will just expand it right away. So I have log of nk plus gk factorial minus log of nk minus log of gk factorial. Okay, and then I do Stirling approximation. So this sum of k is here. I have nk plus gk log of nk plus gk minus nk plus gk. Okay, and then I have minus nk log nk minus nk, but there's a minus sign, so this becomes plus. And likewise, I have this gk, but gk is anyway, I want to write it first. Okay, so this is Stirling. And you see nice cancellation straight away. So you can have this minus nk plus nk minus gk plus gk. So this cancel. Okay. Okay, and the next is you do the differential. D log. Now, always remember, you are doing differential against this nk. Okay, so you first you get the sum again. So you get the sum, and then you have this dnk. Okay, and nothing else. Okay, so let's do it. You have the first term nk plus gk. You use the product rule and you differentiate log, and this is nk plus gk. See, another nice cancellation. Plus, you keep the log, nk plus gk, and you differentiate this term and you get 1. And this term is gone, and you have this nk, dnk is outside. So you keep nk and you differentiate log, and then you keep the log. And you differentiate nk, you get 1 again. And then gk, you differentiate, you get 0. Okay, and then you get this, this is plus 1, this is minus 1. Again, you can kill it. Okay, so this is gone. Sorry, this is 1, this is minus 1. Okay, so they cancel. Okay, so you have sum over k d and k, and then log of nk plus gk minus nk. Okay, and this is the term you need to set to 0 together with the constraint for micro-canonical ensemble. So what I would do is I would do d log. Okay, my sign convention is this. I'm going to use positive alpha and negative beta. Okay, so this is consistent with the note and consistent with previous parts. Okay, so the first term is you have sum over k d and k log of nk plus gk divided by nk plus alpha. So this is alpha sum over k d and k, which is here, and minus beta epsilon k. Okay, it's the same thing again, and this has to be 0. Okay, and in the spirit of Lagrange multiplier, don't say too much, and here you can just extract the term. This nk plus gk Okay, the long argument was given before. So if you are not sure, you should go back to look at that. So I have minus alpha plus beta epsilon k. Okay, so I have to extract the exponential. So 1 plus gk over nk is exponential of this whole thing. Okay, so where are we? This one. Okay, I can drag it up a little bit. So the end result is nk divided by gk is 1 over exponential minus alpha plus beta minus 1. Okay, so this is the end result. This is Bose-Einstein. Where alpha is, so I will write here for you. Okay, I will do it a little bit. I will do it later. So I want you to look at this. First, suppose you have done the other one correctly. To get the fermion case, you will get nk. So this is, sorry. You get nk divided by gk is 1 divided by exponential of minus alpha plus 1. So this is Fermi-Dirac. Okay, I didn't show you how to do it, but you will get this answer. Okay, and now for both expression, alpha takes the form of mu divided by kbt, and beta is 1 over kbt. Okay, this beta is like what we discussed before, and this alpha you have to trust me. At the level of this treatment, is not easy to really give you this form. This is chemical potential. So let's just use it, and bear in mind that if you really want to do this, you need to use a different ensemble. It's not difficult to appreciate this point. Even in thermodynamics, we did something like this. We started by talking about an isolated system. We did not allow particle exchange, but when we introduced chemical potential, we had to allow particle to flow in, and we had to modify the work term to introduce this chemical potential. And therefore, very similar here for this case, for this ensemble, if we really want to get this form, we need to do a lot more work. Okay, and right now my focus is to learn how to use this. So I will just quote this result, and you can look it up and see how to get this mu, but this is the correct form. Okay, so this is the chemical potential divided by kBT. Okay, so you see these two forms here. Another thing you should bear in mind is just this tiny difference here. This -1 and +1, that is already enough to make the huge difference. Okay, so fermions, when we talk about electrons in metals, we use the bottom one, we use the red one. When we talk about phonons and photons, we use the top one. And when we talk about condensate, Bose-Einstein condensate, we use the top one again. So it's important that you do not miss this one here. Okay, so this is one comment. The other comment is about this chemical potential term. And this chemical potential, for future reference, I want you to remember this chemical potential is related to the Lagrange multiplier alpha. Okay, so remember, alpha goes with number, beta goes with energy. It's like a song that you can sing every day. Okay, now if I have a system that does not conserve the number of particles, but still is a closed system, but the number of particles is not conserved, then alpha has to be 0 because alpha goes with dn, right? Up here, where is this? Alpha goes with dn. Okay, so if I do not have particle conservation, I have to set my alpha to 0 because this should not even enter to begin with. Okay, and in this case, when can you have this kind of situation? You have this kind of situation when you discuss photons. There you can create photons. Let's say you have a cavity. You can actually create photons inside your cavity. You cannot create particle with mass, but this kind of virtual particles can be created. Another thing is phonons. It's also something you can create. You can excite the lattice wave, and that will, depending on the situation, the temperatures, this kind of lattice wave can be discussed in terms of the language of particles, and these particles is phonon. The wave language is lattice wave, the particle language is phonons, and these phonons can be created or destroyed. And for those systems, we do not need to worry about the alpha. Okay, so this is for future reference, but not too future. We will see it very soon. We are going to use the Bose-Einstein statistics without this alpha term to discuss phonon and photons. Okay, this is the second comment. I didn't write it down, but that should be in my note. And the third comment is, if you look at these two expressions in front of you, is there are more you can say, right? Because look, if you look at this Fermi-Dirac distribution, the FD, what can I say about the ratio of this number? One thing I can say is this. Now, suppose I have energy states. I can put either fermion or no fermion. Let's say I put fermion here and here, right, for fermion. Or I can put no fermion. I cannot put two fermions. So the conclusion is this: my NK, the number of fermion, compare with the number of states, I have to satisfy this requirement, right? I can have at most the same number of fermions as the number of available states. That's it. I cannot go beyond that. And that explains this +1 here. Okay, so that is to say this ratio, NK divided by GK, has to be at most 1. Okay, so if you look at this factor here, to guarantee this, the denominator better be larger than 1. Okay, and this is one way to remember this +1. Okay, so this is the third comment. And the fourth comment is this. If I raise the temperature, to high temperature to the classical limit again, there's no difference between fermions and boson anymore. Okay, they are still different, but we don't need to worry about the difference. That's why we have this classical limit again. Okay, so how do I integrate this knowledge into these two expressions on your screen? You look at these two, and you see the only difference is this -1 and +1. So using that argument, so this is important enough. Let's write this down. So this is not the same. Yeah. So classical limit, classical limit. Okay, in the classical limit, no difference. Okay, let me be more precise. I cannot erase. Okay, they are different, but no need to differentiate. Fermions versus boson. Okay, so in other words, they should be described by the same statistics. So if you look at these, the only difference is this plus and minus 1. I must as well kill the constant here. Okay, so I can write it like this. So the classical limit, I must have something like that, such that the difference between the two statistics will be gone, because now I just set them to be this constant. You can think of it as plus lambda. Lambda equals minus 1 is Bose-Einstein, plus 1 is Fermi-Dirac. I will just set it to 0. Then there's no difference between them. Okay, and indeed, this is, you see, this immediately gives you your Boltzmann factor. Okay, you might not be too happy about this argument. Another way to argue about this is the following. In the classical limit, remember what we have. So in the classical limit, we really demand the number of particles is much lower than the number of states. Be careful, this is not the same as this. If you have eyesight problem, you need to fix it. And this is for fermion. This is in the dilute limit. So this is the dilute limit. In the dilute limit, in order to satisfy this, and this is much lower than this, so this whole expression has to be much lower than 1. Okay, and the denominator has to be much larger than 1. If this is much larger than 1, do I care about this tiny correction of plus or minus 1? No. I have a huge number here. I don't care whether it's 1 million minus 1 or 1 million plus 1. So I will ignore this 1 and I will recover this. So this is another way to look at this. Okay, so this is a classical limit. And with this, I actually finished this chapter. This chapter 11, as I say, is very brief. And what we really need to do is to get these two statistics and learn how to use them. Okay, so I will give you a quick preview, then I will let you go. I will post the notes for the next chapter. This is chapter 12. So chapter 12 is about Fermi gas. I'm going to start from the Fermi-Dirac distribution. So I want to talk about a gas of fermion, or another word for describing, another term for this is Fermi gas. Okay, and it turns out that the best example is electrons in metals. Okay, this part has a little bit of solid state physics flavor, because we are really talking about a very important class of solid state material, metals, and we are talking about the mobile electrons in these metals. Okay, why this requires Fermi-Dirac? Again, this is the third time I say this, so you need to estimate the number density of electrons. Okay, and you need to estimate NQ for electrons. Okay, and even at room temperature, you realize you need to use quantum statistics. Okay, so you do this and then you compare N and NQ and sub Q. So this is assignment problem. Just as an aside, this is also the reason why I talk about metals. Without much solid state physics, I cannot say too much. But there's another class of materials, semiconductors, which is also conducting. Okay, semiconductors, You can conduct electricity. Metals, you can conduct electricity. At room temperature, if I give you a piece of material and ask you whether this is metal or semiconductor, it's not that easy for you to tell me. Okay, unless you already know the compound name. Okay, I give you a piece of lump of sample and ask you what is this. It's not that easy to discuss. And to do it properly, you need to cool down, and you want to do some good low temperature physics to find out. But just as an aside, if I take a semiconductor and repeat this exercise, okay, I still have electron. Look, I still have electron for this problem, but now I have a semiconductor. And you realize at room temperature, you can use classical statistics. Okay, so this word has a lot of profound implication. If I have a semiconductor, I don't need quantum statistics at room temperature. Okay, and that's why I say to find out you need to cool down, because at low temperature things will change very differently. Okay, so coming back to metals, this is the focus of this chapter. We are not going to talk about other conductors, for example, semiconductors. Coming back to metals. So the history is this. So J.J. Thomson discovered electrons, and 3 years later, so in 1897, this is the discovery of electron. And then 3 years later, this is by J.J. Thomson. And after Thomson's discovery, 3 years later, so there's 1900, this is way before quantum mechanics. Schrödinger equation is about 1920. Here, Paul Drude already applied, uses kinetic theory of gases. Kinetic theory of gases to describe this problem. So you can kind of sense what is going to come up. This model has some success, and today we know which part can be used, which part are going to fail, and I will tell you which part will guarantee to fail. This so-called Drude model failed to explain why the heat capacity due to electron is so small. You see, heat capacity plays a role, right? As a student of thermodynamics, you should be happy. You learn how to do heat capacity. Heat capacity in diamond motivated the Einstein model, and heat capacity in electrons motivates something else, and that is the quantum statistics treatment. Here, this is wrong. It's not because of the physical picture. The physical picture is okay. Kinetic theory of gases assume you have electrons as ideal gas. So these electrons are non-interacting. They are bound in the potential, and this potential is due to the sample. The electrons, we assume when we do this kind of experiment, the electrons do not escape. Okay, so this is like a box, a free electron model. So this picture is okay, there's nothing wrong. So what went wrong was the fact that the classical statistics was used. Okay, so here in this picture, so Drude prediction. The heat capacity due to electron is 3/2 NKB. Now this shouldn't be surprising, because today's lecture we talk about U is 3/2 NKBT. If you just take the derivative, if you treat electrons as classical gas, you get this right away. But this is a huge heat capacity. Why? Because the Dulong-Petit result, Dulong-Petit, tells you the heat capacity in the Dulong-Petit is 3R. Right, Dulong-Petit, at high temperature limit, at classical limit. Okay, and I told you Dulong-Petit was well tested in the classical regime. If you go to high enough temperature, you will see this 3R. Okay, this is what is this? This is molar heat capacity. Okay, now let's convert this to molar heat capacity. So if I have 1 mole of electron, I will have 3/2 times MA times KB, and this is 3/2 times R, where R is the gas constant. So the point is this: if I'm able to detect this much heat capacity with good enough experimental resolution, don't tell me I cannot detect half of this amount. Okay, so if this contribution due to electron is indeed there, it would have been discovered long ago. But this is simply missing, it's not there. Okay, so the Drude prediction is way too large. This number is way too large. And our goal is to explain properly why the actual contribution is much lower than this amount. Okay, so need to use Fermi-Dirac properly. Now, this comes from Maxwell distribution. We already saw it last time. So we need to use Fermi-Dirac statistics to analyze the problem. To analyze the problem again. Okay, so I'm going to stop here today and pick up from this point where we are going to use the result from here. So I'm going to take this, I'm going to switch to continuum limit, and I'm going to really just play with this expression to show you how to solve this problem. Okay? All right, so that's it for today. I will see you on Wednesday. Thank you.